minus 1A.
All right, let me just go ahead and start. Any questions about what we've covered so far? By the way, thank you for recording this. I mean that seriously. Thank you. Have you all looked at these things online? Anybody? They're good. That's high quality, man. I get something out of it seeing my mistakes. Any questions about the homework at all? I gave you several polarization ones, right? And they were you just plot a few points. You figure it out. I don't really care for a lot of things that have to do with formulas that you try to derive the polarization from that. Just plot 3 or 4 points. You can figure it out in a heartbeat. No other questions? Yes.
I have a question. Whenever the second term is over 180, does it go the opposite polarization?
You're asking, it's hard for everybody to understand, but here's what it's saying. If you have an electric field, and let's say it's propagating in the z direction, let's just get rid of that. Propagating the z. So this is going to be xy components of it. So we're going to have some E naught of x, right? It's just a constant, times cosine of omega t, and I always make z equals 0, so I don't have that beta z term in there. So you have omega t, right, ax, and then you have plus some E naught y cosine of omega t plus some phase angle, plus or minus some phase angle, ay. Now his question is, just by looking at that, can you figure out the way it's right-handed or left-handed? Right? Frankly, yes, but plot the points anyway. The minute I see a plus on the phase term, it's a positive there, I know it's moving in the clockwise direction. The movie I see a minus, it's moving counterclockwise. But to be safe, plot 2 or 3 points, the way I've done it. Because people mess these up all the time. There's all these little rules that Dr. Wentworth's book has. When you put it in the phasor domain, there's certain terms, if they're positive, it goes one way, certain terms, it's negative, it goes the other. And here's the other thing. This doesn't have to be this equation. This could be a sine, all right? It could be a sine of omega t plus another phase angle, call it theta, right? Now, really, the only way you figure that out is plot. All right, remember that, because there's going to be all sorts of questions like that in time. You'll have to be aware of. It's plot 3 points, let omega t be 0, 45 degrees, and 90, and it'll tell you everything you need to know. All right, that's not a bad question.
I just meant if the phase is over 180
or if it's anytime you get something, let me just say, if you have a cosine of theta, if you have cosine of theta plus or minus 180 degrees, that's minus cosine of theta. Do you understand that? So if you want to absorb a minus sign into a cosine function, you just add or subtract 180 degrees. What did you want to say about the 180 degrees? If you add exactly 180 degrees of phase, will it change the direction? Is that what your question was?
Just 6.32, it had 10 cosine of omega t minus, whatever, and then it had minus 20 cosine of omega t minus 45 degrees, and you add the 180 or whatever to switch it from a minus to a plus cosine. Does that?
I would have to plot that one.
Okay.
I'm going to tell you, I'm not certain, but they're not hard problems if you just plot. Any other? I mean, I'll do that one if you want me to, but it's just. You want me to? Give me the equation.
10 cosine omega t minus beta z.
What? Minus beta z, did you say?
Yeah, minus beta z. AX.
Okay, we're going to get rid of that now.
And then minus 20 cosine omega
cosine?
t. Yeah, cosine.
Go ahead.
Omega t minus beta z minus 45 degrees.
By pi over 4. See, this is going to be radians. That's why I don't put degrees in there.
Yeah.
And that's AY, right?
Mm-hmm.
All right, so right off the bat, when you're looking at this, let z be 0. That way, I get rid of this beta z. You don't like beta z if you don't need beta z. Now, here's a simple thing. You start here, let omega t be equal to 0 degrees, right? One look here, this is going to be the x-axis, this is the y. I'm plotting this vector, so I'm plotting the magnitudes of EX, the EX component, and the AY component. look here, when omega t is 0, cosine of 0 is 1, it's 10, right? So out here we have 10. This is an omega t equals 0. Do you agree, everyone? Can you all see that in the back, guys? I can barely see you guys back there. And then over here, now, he says, why don't we do this? Make that positive and add 180 degrees or subtract 180 degrees. All right, it's already at minus 45, right? If you add, say I add or subtract 180 degrees from there, what do I get? Well, 45 and 180 is what? Think about that. That's 2 what?
225.
2 what?
225.
So, I think, all right, we'll do it with degrees. So this could be minus 225 degrees, right? Now, I got to remind everybody about cosine and myself. When I do this, I always draw one of these things out. This right here is 0. That's pi over 2. That's pi. I come out of here. Sorry, this is pi. Boy, I drew that thing not quite right. This should be pi. That's minus 1. And this should be 3/2 pi, and this should be 2 pi right here at this point. Now, when I look at this, if I'm evaluating, because now I'm going to be omega t 0, so it's cosine of 225, that's 180, right? 225 is out here somewhere, right? Is that 1 over the square root of 2? 0.707? You can check. It's minus 0.707 times the 20 in front. So that means here, the y value is actually negative down here. And if you look at this, I'm just going to estimate. That's the first hand at omega t equals 0. Can everybody see what I'm doing here? You understand? I'm just plotting two vectors. So this is omega t equals 0. Next, I let omega t, in this case, be, just say it's going to be pi over 4, all right, 45. So I'm going to let omega t be equal to 45 degrees or pi over 4. Now, the cosine of, and by the way, you can see that the amplitude, I know it's going to be elliptical just because these have unequal amplitudes, almost guaranteed elliptical. I just want to see which way the hands of the clock are moving. Next, well, I know when I have 45 degrees here, right? Cosine of 45 is 0.707 or 1 over square root of 2. So this comes down, it's going to come down to like 7.07, right? What about this one? Take a look. Now I'm going to have 20 cosine of omega t is now 45 degrees. 45 minus 225, 180, right? Cosine of 180 is minus 1, right? And times 20. So now this thing is getting bigger, and you can see what happened is the hands of the clock are moving in this direction, correct? Y'all see that? They're moving clockwise. Now take your right hand, put it in the direction of propagation, right? And you'll see it is moving what? Left hand elliptical polarization. Do you see that, US? Do you all see it? It's moving this way, so it's left hand, right? Because if I take the thumb on my left hand, put it in the direction of propagation, X, Y, Z's out of the board, right? So if the left hand, the hands of the clock are clockwise, like I'm closing the door with the thumb in my left hand pointing in the direction of propagation, I go from 1 to 2, this is 0.2, so it'd be left hand elliptical. Is that what he has? But I always plot him. I don't play the games he does now. Because in the real world, here's what you get. You're going to have measurements that you're going to look at. You're not going to be looking at equations. That's the way it's really done. You'll have snapshots in time, measurements of the electric field. All right. Any other questions about the homework? About reflection?
You use 639.
Say again?
639.
Yeah, we'll do it. Now these waveforms for the reflection and the transmission, this is called normal incidence. It means the wave is moving straight in, normal, to the surface. We're going to take a look at oblique incidence in a bit. That's more important general case. But here, all right, give me the specifics of this problem. Which is the number again?
639.
39. Give me the specifics if you don't mind.
It says in air, an average power density of milliwatts.
All right, so we have P, let me just write it down. we have 100 milliwatts per meter squared as the power density, go ahead, and it's in air, which is nice, so that means eta is just equal to eta naught, or 120 pi ohms, right? Go ahead.
And it's saying it's incident on a non-magnetic material.
All right, so now, here's the incident waveform coming, where E, and this is non-magnetic, so that means mu is just mu naught. Go ahead. This is material 1, this is material 2.
This is permittivity is equal to 11.
All right. Epsilon relative equals 11. The relative permittivity is 11. Go ahead.
And it's saying what are the average power densities that would be reflected and transmitted?
All right. For this one, pay attention to this one. This is a good problem. It's a classic kind of problem. Makes you think. It's testing if you truly understand what you're doing because of your how to get different things from this basic information. Now, in general, we know that PAV, right, is equal to really 1/2 the real part of E crossed into H conjugate. Remember, that's the general form. We have neither of those, correct? But we know something, that we're in air, and eta naught is 120 pi, right? And in air, for all intents and purposes, we can assume sigma is 0, meaning alpha is 0. Follow me? Now, because of that, the actual value of eta naught is the magnitude of E naught over the magnitude of H naught, right? Isn't that right, guys? How many see that? Now, we know from this equation, and I'll put it up here, that what that actually reduces to when you put the correct values of E and H in, I mean, you substitute for H, E naught over eta, right? With e to the minus j beta z, and then you take the conjugate of it. What this will become is 1/2 the magnitude of E naught squared, that's an incident field, over the magnitude of eta naught, times the cosine of the angle associated with eta naught, right? And then it would be normally e to the minus 2 alpha z here, AZ, it's propagating in the z direction. But because eta is eta naught, this cosine term, this angle is 0. So the cosine term goes away, and this goes away because alpha is 0 in air. You follow me? Now here's the reason I'm doing it that way for a reason. So you know, if you're dealing with a lossless media, then you can say the average power density, I'll put it right here. This is for a lossless media. And air is a good example. That you can say PAV here is just 1/2 the magnitude of the E field squared over eta in the AZ direction if it's propagating in AZ. If it's air, it's just eta naught. Why did I say that? Because since we're given PAV, we can get the E field. We can see that the E field itself, its magnitude, would be equal to 2 times eta naught times PAV, right? And simply the square root of that. Can somebody give me that? I want to do this whole problem. It's a good problem. Y'all see what I'm doing? I'm giving the power density, now I'm getting the E field, because I know the constitutive parameters of the region. Yeah?
What was that stuff you crossed out? Just a second.
The cosine of the angle of eta. Eta is strict real, right? The angle is 0 degrees. Give me the E field. Who asked that? Somebody asked it. Oh, you did. All right. I'm just trying to show you the steps. Because I'll ask questions like this. I ask for the E field here, the H field there, the E field, the H field, all this stuff. Anybody? And I appreciate you bringing calculators to class. I think you.
It's 274.58
274
milliamp.
millivolts per meter.
No,
274, 0.274 volts per meter. I'm assuming that's right, right? Right? Now, I wanted to make sure I break down this. I'll show you the power formula in a second. So that's the incident field, right? Now, what is the reflection coefficient at the boundary? And what is the transmission coefficient? Well, the reflection coefficient, I did this last time, and I was just at the end of class, and I set it up, but I gave you the final form, right? Do you remember this class? How many do? This is the reflection coefficient, very important. Right here, it's always going to be the impedance you're going into, so it's eta 2 minus the impedance you're coming from, divided by the sum. Now, specifically, we need the impedance of the second region, don't we? Y'all agree with that? Can you all see it back there, what I'm doing? Now listen to me carefully and you'll get it. Well, what is the impedance or the characteristic impedance? Intrinsic impedance, pardon me. It's equal to the square root, normally it's j omega mu over sigma plus j omega epsilon, right? That's the general formula that you put in your head. But when sigma is 0, you'll notice the j omegas cancel, right? And you're left with what? The intrinsic impedance of the region is just equal to the square root of mu relative over epsilon relative times the square root of mu naught over epsilon naught. And I'll get out of your way, the square root of mu naught over epsilon naught is just eta naught, isn't it? So leave it as that eta naught. And then it's times the square root, well, mu relative is 1, and epsilon relative is 11. That's a bad number. All right, you with me on this one? So now I've got, it's really eta naught over the square root of 11. I don't need a number. Eta naught over the square root of 11 is going to be equal to the region 2 in characteristic impedance. So this becomes equal to eta naught over the square root of 11 minus eta naught over eta naught over the square root of 11 plus eta naught. I'm just putting in the values. The reason I left it in terms of eta naught is what? Take a look. What do you notice that happens to it? Class? It cancels. It goes away. So really I have 1 over the square root of 11 minus 1, and then 1 over the square root of 11 plus 1. And can anybody tell me what that is? It's going to be negative, but I don't know how negative.
Negative 0.537.
0.
537.
Minus 0.527.
37.
37. So now I have the reflection coefficient, right? That's the reflection coefficient. What do I do to get the transmission coefficient if I have the reflection coefficient for normal incidence wave?
1.7.
Just 1 plus it, right. So we get tau equal to 1 plus that, and what is that going to be?
0.995.
Pardon me?
0.463.
It's 1 minus that is 0.463. So now I have the transmission coefficient. Agreed? Class? Let me show you something now. All right, now that we have those two, I'm going to come back over here and just use this part of the board to finish this problem. So now what I find is my transmitted power density. First I find that E transmitted would be equal to E naught incident, right, times the transmission coefficient. I have the incident field, right, and I have the incident field we figured out was right here. This is E incident. Right? So, and I've got the transmission coefficient. I find the transmitted field, give me this too, is E naught, which is equal to 0.274, times the transmission coefficient, which is 0.463. And what do you get for the transmitted field? 0.127. And the reflected field here is going to be equal to the reflection coefficient, which is equal to minus 0.537 times the incident electric field, which is 0.274. And what do you get for the reflected field?
Negative 0.147.
Minus 0.147. And this volts per meter, by the way. Can everybody follow me on what I'm doing here? I'm just going through it methodically, so I'm getting, yeah.
Oh, I'm sorry, but is that transmission coefficient, is that a tau?
Right here, yeah.
Yeah.
That's the transmission coefficient.
No, I was just asking what the symbol
Yeah,
is.
forgive me for my handwriting. It's
Okay.
tau.
Okay, I'm just making sure.
Yell at me if you need me to make it better or clarify. Are you with me on these things? Now that we have the E field in every region, we have eta in every region, we can get the power density reflected. P reflected, I can call it REF if you want, is just going to be 1/2, always this formula if it's lossless, magnitude of the reflected field. Well, that's the reflected field, right? The magnitude would be 0.147. So it's 0.147. Then you square that and divide it by eta. Eta in this case is just 120 pi. And that will be the power density in watts per meter squared. The second thing you get is P transmitted. And that would be 1/2 the E field that's transmitted, which is 0.127 squared divided by eta. Well, eta in that one isn't eta naught. It's going to be 120 pi, right? But it's divided by the square root of 11. Y'all follow me on that, class? So now you've got this power density. I want to show you something. Give me these numbers too. Can you give me P reflected, please? And I appreciate you doing it.
It is 0.0286 milliwatts.
Say that again.
0.0286 milliwatts.
286 milliwatts. So it's milliwatts per meter squared. 0.286 milliwatts per meter squared. And what's this one, P Tran?
0.095 milliwatts per meter squared.
0.095 milliwatts per meter squared. All right? Got me? Now watch. Common sense tells you incident power minus reflected power should be transmitted power. Do you all agree with that? And in fact, it bears out. If you actually do the numbers, if you take the incident power density, which was, where the heck was it? It was up here a second ago. 100 milliwatts per meter squared, right? If you take this, P av, P incident, and you subtract P reflected from it, you will get P transmitted. Follow me on that? Go ahead and do it if you don't believe me. Just take P 100 milliwatts minus, was it 100 milliwatts? That doesn't look right at all. If it's 100 milliwatts, we can't have fractions of a milliwatt reflected and transmitted. Some number here got goofy, and I'm trying to figure out, is this right here?
Yeah, that's
Huh? That's right? Or?
no. Wrong.
Well, it's wrong. Well, there we go. What is that?
8.68.
Thank you so much. 8.68 volts per meter. And guess what? Now we have to go through it and change all the numbers. I'm sorry. I appreciate that. But let me show you something. You can change the numbers. It works, what I'm showing you. How to get the electric field is based on what. This is the real thing. All right. Now, remember that we know that E naught incident plus E naught reflected is equal to E naught transmitted. That's true. That's also based on the fact 1 plus the reflection coefficient is equal to the transmission coefficient. Are you with me on this? That here is based on this, because we define reflection coefficient as a ratio of reflected to incident field strength. Got me on this, everyone? And tau, the transmission coefficient, is really E naught transmitted by EI. So we just take E naught I and divide that equation, we get this equation. Now, listen, that's true. Here's another thing if it's true. P incident, and this is only for normal incidents, so only for normal incidents. This is not true in general for oblique incidents. So P incident, or P, I put it INC, P incident minus P reflected is equal to P transmitted. Common sense tells you that. All right? It does. And we can prove that in many ways, but I'm just going to write the equation. Well, the incident power density, all right, is going to be 1/2 times magnitude of eta incident squared over eta, right here, over, call it eta 1, minus 1/2, and then here the reflected power density is really magnitude of gamma right here times E naught incident squared over eta 1. And the transmitted power density is 1/2 times the magnitude of the transmission coefficient times E naught incident squared over eta 2. Now, go ahead and look at that. I've simply substituted in terms of the E field and transmission or reflection coefficients for the incident, reflected, and transmitted power density. This is incident, this is reflected, and this is going to be transmitted. You all see that? Can you all see this, class? Now, my next step is pretty straightforward. I'm going to divide E naught incident out. Get rid of it. Follow me? Once I do that, I see what I have. Well, let me do another thing too. You see this by now. I'm going to multiply everything by 2 before I do anything more. Then I'll divide E naught incident out. So I have really 1 over eta 1 minus, I got rid of the half too, minus magnitude of gamma squared over eta 1 is equal to tau squared over eta 2. Can you all follow me on what I'm doing? Everybody? Now multiply both sides by eta 2, eta 1. And here finally I get, hope you can read this, eta 2 times the quantity 1 minus magnitude of the reflection coefficient squared is equal to eta 1 times magnitude of the transmission coefficient squared. But really I got that not because I'm going to sit there and memorize this stuff, because I know the incident power density minus the reflected power density is equal to the transmitted power density. Follow me on this, class? And that's where its basis is. And are those answers, well, we had a bit of a false start here. But if you take that number and multiply it by gamma and then square it and divide by eta 1, take that and subtract from 100 milliwatts, you'll get the transmitted power. How many see what I'm doing right here? Are you good with this? In the back, can you guys see it? You with me on this? All right. That's not a bad one to do, actually, because it's talking about power relation to E field, and it's really important you do that. Out of curiosity, somebody tell me, how would I get the H field in this region? In region 1, if I had the E field. Suppose I had the E field as this. I know I'm in free space. How do I get the magnitude of the H field anyway?
1 over eta cross V?
Well, we just take the E field and divide it by eta. I want you to guys get into thinking about the relationship between E and H like V and I. All right? All right, think about this. If you have a resistor R and you have a voltage across it V, you know that the current I is equal to just V over R. If they give you any two of the three, V, I, or R, you can get the other one, right? Now, when you're dealing with electric fields and H fields, think of E like you would the voltage, think of H like you would the current, and think of eta as you would R. You know that E over H is eta, all right? So if you got the E field and you want the H field, H is simply going to, in magnitude now, I'm talking about magnitude of the actual field, the H field is simply going to be the E field divided by eta. Can you all follow me on this? We got the E field right here. What's eta in region 1? People.
125.
120 pi, right? Just divide that by 120 pi or 377 about, and you get the H field. Follow me? It's important you get familiar with these relationships and you feel very easy by going from one to the other. And so if I gave you the H field here, or the H field here, you could work backwards and get all the other information of the problem. And that's a common thing I do. I want to make sure you're thoroughly familiar with this, so I might come out here and say, if I have an H field in this region, it's propagating this way, and epsilon rel is 11 here, and epsilon rel, and this is just air. I want to know the incident power density, so you would work backwards. Yeah?
Did we see that eta is 125 just in air or any losses?
No, only in air, because remember, the way we got it was right here. We said eta in general is the square root of j omega mu for constant frequency now. This is a constant frequency word, divided by sigma plus j omega epsilon. We're in a lossless media, right? If it's lossless sigma 0, then I get square root of mu r, or mu relative over epsilon relative times square root of mu naught over epsilon naught. That's eta naught. That's 120 pi. And then if you've got either mu or epsilon different, you have to take the square root of the ratios and multiply it by in and out. Okay? Alrighty, good problem. Pity we. What's that? Do you have any, does anybody have another question about that homework? I've always felt doing problems is the way to really achieve understanding of these things. If you don't do them, you really don't know if you know it or not. But you'll figure out you don't know it if you can't do them.
This just was good. So in this case, the surface. Yeah, but the surface doesn't matter. You just trying to find an inch. The first is. Yeah, I think this might always be true. The problem is finding this.
All right. Now today, we're going to go into oblique incidence. That's non-normal incidence. And there's a couple of things I have to tell you. This is more complicated than it needs to be in Dr. Whitmer's book, but it is the most general form. And in the real world, when you deal with radar, when you deal with telecommunications, say you're a microwave engineer, you do microwave links, the field quantities orientation become critical. It becomes absolutely critical. And almost never is it normal incidence when you're talking about transmission over the surface of the Earth. So first, we're going to call this TE polarization. But I got to tell you a little more about it. This means transverse electric field or electromagnetic field. Now I'll tell you what it means. Get a plane together. Just put something here and call this region 1 and call this region 2. In region 1, we're going to have some beta 1 and we're going to have some eta 1. In region 2, we're going to have some beta 2, some eta 2. Follow me on this? So it's a planar region. I'm saying it's a plane right here. Not a very good one, but it's a plane that separates it. Really, the way I like doing is putting it horizontal, because the real way in radar and stuff, we talk about two regions. Usually we talk about waves incident on the Earth. What's below the Earth is one region, above it another. That's very common. So this polarization TE is defined, I got to put a coordinate system in here. Let me call this, let's see, call this Z, and because I want to keep it in terms of the book. So this is going to be Z, and this is going to be X. And if you think about this, since X cross Y is Z, Y is actually out of the board. You all see that, class? Now, follow me carefully on this one. This is a little different. So what we do here is we're going to say, erase this. Something I don't like about that. I want to have this thing crisp right here. Let me do this. This is region 1, this is region 2. Now, so this is where the barrier is. They say if you have a wave, and I'm doing it the way he did it right here, this indicates a wave, that squiggly line, and we have the electric field coming out of the page. So the E field is coming out of the page, all right? Can you all, okay, let me do it this way. I'm trying to show you the E field's coming out of the page. The way they taught this years ago, when I was in college, they said if it's a dot with a circle around it, it's coming out. If it's a cross with a circle around it, it's going in. They got that from archery, because if you look at it, it's something that pierces the target. The tip comes out, and you basically look at it like a hole around it. But if you look from the other way, if feathers go in, it's going in, and you see the cross of the feathers. That's where it came from us. That's my understanding. Now that's the orientation of the E field. E cross H is going to be the direction of propagation. This is the direction of propagation. Do you follow me? And I'll get to that in a second. There's going to be an angle with respect to the normal incidence. It's important you understand this angle is with respect to the normal, called theta. It's called the incident angle. What page is that in your book? You're looking at? Is that in the book right there? Do you have the book online?
No, I don't have the book.
I don't know what page it's on, but you've got your book. What,
361.
say again?
361.
361, page 361 is this drawing I'm trying to draw. Now the H field will be this way. I know the H field will be that way because, follow me, E crossed H is the direction of propagation. Use your right hand, put your index finger in the direction of the E field, then let your thumb be in the direction of the propagation, right? And when you cross E into H, it has to be the direction of propagation. H can only be this way. And by the way, E and H in the direction of propagation are always orthogonal to each other. Can y'all see this? Can y'all? Are you with me on this? So that's the direction of the H field. Don't worry about that. I'll get that in a second. I'm going to prove that. Now there's also going to be a transmitted field. This is the incident. There's going to be some transmitted field. And I guess I better do this like that. So there's some transmitted field. Oh, pardon me. It's coming out of the board. It's the E field's coming out of the board. E transmitted. And it will be at some angle theta transmitted, and there will be some H field, H transmitted. Then there will be a reflected field, right, propagating this way, and I better do it this way. This will be E reflected. And if you look at this, E crossed into H is the direction of propagation that way, so H will be this way, H reflected. His book does a better job, and there'll be an angle of reflection too. You follow me what's going on here, class? I'm just trying to establish a drawing and a coordinate system. This is going to be Z, this is going to be X going up, and Y is coming out of the board. Follow me? Now the next thing I have to do is write in terms of the actual coordinate system and the quantities, expressions for them, phasor expressions. So I want you to watch this right now. First, I'm going to say that this vector direction, I'm going to call Z prime. I know I got Z and I got Z prime and I have X up, right? Now please follow me on this. I'm just going to focus on this quadrant and I'm going to come over here and mention something. Remember, if that is Z and this is X, then if you think about it, when I have my Z prime here, I have a certain distance in X. I have, this is the angle, right? Can you follow me? Just watch this. This is my Z prime, this length. I took an arbitrary length. There's an arbitrary X right there. Now listen, the projection of this X onto here, right to here, would be equal to X, right? And if you look at this, pardon me. This is theta. This is theta. My bad. That's theta incident. That's going to be, this distance from here to here would be X times the sine of theta incident. Now, let me see how to show you that. I'm sorry, this is Z, my bad. That's Z. And that would be, this distance right here would be Z times cosine of theta incident. Because if this is theta, opposite interior, this is theta right here too, remember geometry, not opposite interior, but this angle will be theta as well, and theta incident, and then the projection on the near side to the angle right here would be the cosine, that's Z cosine. Now this distance here, well, if you look at that, that is X, right? From here to here. So this distance right here, from here to here, I'm trying to show you this, like right here, this is going to be X times the sine of theta incident. Can you all see that? That means my Z prime is equal to Z cosine theta incident plus X sine of theta incident. Now I'm going to tell you right now, it takes a while to look at this stuff to appreciate it. If you're not thoroughly convinced of that, you're not alone. Take some time to convince yourself it is true. I guarantee it. Now, a unit vector in the direction of propagation, right here, I'm coming back. A unit vector in this direction, AP incident, maybe I better put it up here so you can see it. AP P incident would be equal to cosine of theta incident times AZ plus sine of theta incident AX. Now I'm going to stop for a moment and convince you of this. This one's easier to see. All right, if it's coming in normally incident, if it's coming in where the incident angle is 0 degrees, you all agree that would be normally incident? If theta is 0, class? Take a look at this. The unit vector would be cosine of 0 AZ, or just 1 AZ, right? Sine of 0 is 0 and no AX. Do y'all follow me? So it checks, it makes sense. What if the wave is coming straight up in the X direction? What would theta be? Theta incident. Class? Can you all see that this is theta incident? It's measured from the normal to this point. What would theta be? 90 degrees, right? Now that means if it's going up, AP should be in the X direction. In fact, it is. Cosine of 90 is 0. There's no AX component to the direction, unit vector in the direction of propagation. Sine of 90 is 1. It's all in the X, right? This unit vector works. All right, so that's the unit vector in the direction of propagation. I'm going to add one other thing about this. We can get a unit vector in the direction of transmission by the same exact formula, only putting theta t there. Right? So I'm going to go ahead and say AP transmitted would just be cosine theta transmitted AZ plus sine theta transmitted AX. Got that one knocked off. And then I'm going to say for the reflected field, A, and I'm going to call it P and R. Well, that's going to have this same form, cosine of theta reflected, but it'll have a minus sign in front of it. And here's the reason. The reflected wave is in the minus AZ direction. Do you follow me? So it's minus, let me write that a little better, minus cosine of theta reflected AY, and it will still be a positive component of X plus sine of theta reflected AX. So those are the formulas that I'm going to start using to describe these fields. I had to go through this with you. But this is a little more complicated. Yeah?
On the reflected, should it be AZ instead of AY? Or is that
AZ, that's supposed to be a Z. You're absolutely right.
Okay.
That's AZ, thank you. Thank you so much, AZ. My bad. Y'all get that? Now watch. Here's how we do this. This is a TE wave, and I've got to make mention of a few things. The whole idea with the TE wave is this. The electric field is perpendicular to the plane the wave is traveling. Here's an easier way to remember it, in my opinion. When we do this with radar, we always call this parallel polarization, and here's why. The electric field is parallel to the actual surface, the boundary it's hitting. Can y'all see that? If this plane extends out of the board forever, right? When it hits this plane, the E field's in this direction, it hits, the E field's it's parallel to that plane, right? Or horizontal. We call it horizontal polarization because almost always, when you're talking about radar and things like that, the Earth is horizontal, right? And if the electric field is like this, can you all see it's horizontally oriented, right? If it's out of the board. So I call this horizontal polarization. The book calls it transverse electric because the electric field is perpendicular actually to the direction of propagation. That's the reason in the plane. Following? Now you can say, well, what about the H field? It's there. Well, the H field is not perpendicular, all right, if you look at this to the direction of propagation, because this field's going this way, right? Just take a look at this. You all see how there's a component of the H field in the direction of propagation? All right, but just remember, you look at the E field when you want polarization. Perpendicular is TE, right? He calls it perpendicular, he calls it transverse. You can call it perpendicular polarization. In his book, who has it open? What does he term it? Is it perpendicular TE? Does he TE? Just TE. That's fine. Now, here's how they go about defining the field quantities. First, they do the electric field. Write this down. They're going to have incident electric field in general is given as some E naught incident. Then it's going to be E to the minus J beta Z prime. That's my Z prime over there in the AY direction. It also means when I put in what Z prime is, it's some E naught incident times e to the minus j beta, and this is beta 1, and then it's going to be z cosine theta incident plus x sine theta incident. And that's going to be ay. So he replaced the z prime with that. This is why it gets a little tedious, a lot of that thing's repeated over and over again. So I just put z prime. And you can call it z prime incident too, if you want, right here. Now, the h field that's incident, you get by this. You take 1 over eta 1, unit vector in the direction of propagation, that's the actual incident field, crossed into E incident, right? I'm going to use that formula. It's very common. We're going to use it. Now, we could take the curl of E and getting it, right? Curl of E divided by minus j omega mu, but that's a pain, so we're going to do this, all right? And that's the way his book does it. When we do this, I'm going to go ahead and just crank this for you. So I'll only do it once, I think, here. It's 1 over eta 1 times E. Well, then E is this, isn't it, class? So I'm going to take the E naught incident times e to the minus j beta 1 z cosine theta incident plus x sine of theta incident here. I'm going to divide it by eta 1. And then, if you'll notice, now I have to take a unit vector in the direction of propagation, which was my cosine of theta incident a z plus sine of theta incident ax, and I have to take that and cross it in with ay. I'm going to stop here and let you appreciate this. Can you all see what I've done is I factored out the scalar variables e naught incident over eta 1. I've left the exponential e to the minus j beta 1 z cosine theta incident plus x sine theta incident in there. You all see that, class? And then I've gone ahead and written this. Now, when you do the cross product, this is the last step. I had to take the unit vector in the direction of propagation crossed into the E field, which is just AY. Follow me? When you do it, AZ crossed AY is minus AX. Do you see that? And then I have AX crossed AY is positive AZ. So what I can do here, so I don't have to rewrite the whole thing again, I can actually say since AZ crossed AY is minus AX, I'll put minus AX here, or minus this AX. And since X cross Y is AZ, I'll just put plus AZ here. And that will be the H field expression he has. Can you confirm that, whoever has an open book? Yeah? You've got your book on. You see it?
That's good.
You see it right there? Now, he's going to do the same thing for the rest of them. And I'm running out of time, but I'm just going to show you this. For the transmitted field, just bear with me. I'm trying to make it easy, all right? For the transmitted field, he's going to call this E naught transmitted over eta 1. Or, I'm sorry, E naught transmitted, period. Then it's going to be times e to the minus j beta 2. Then it's going to be z cosine theta transmitted plus x sine of theta transmitted here, AY. Then he's going to get H transmitted doing the same little trick here. He's going to do this. I'm not going to go, I don't have time, frankly, to write that crossing out. I'm just going to give you the answer. You take this answer, see this? The only thing you do is replace theta incident with theta transmitted, eta 1 with eta 2, and beta with beta 2, beta 1, beta 2. That's all you do. So now you get E naught transmitted times e to the minus, I always hated doing this one in class, minus j beta 2 times z cosine of theta transmitted plus x times sine of theta transmitted right here. And then I got to have divided by eta 2. Remember it's eta 2 because it's transmitted. And then it's going to be still, it's going to have minus cosine theta incident AX, that's right, AX minus cosine theta incidence AX plus sine theta incident AZ. All right, we've got 2 of the 3. I'm out of time, but I'm still there. Finally, the reflected field. E naught reflected, just let me do this and we'll be happy together. I'll be happy at least. Minus j beta 1. All right, now here, you got to understand, z's going the other way. So there's two ways to do it. I just do it minus z cosine theta reflected, and it's plus x times sine theta reflected here, and it's ay. That is going to be er. For hr, here's the thing. For hr, what happens is, remember the unit vector is has a z component that's, where the heck is it? Do I put, reflected, it's minus that cosine, all right? So when all is said and done, if you look there, he's going to have E naught reflected over eta 1, e to the minus j beta 1, and it's still going to be, I'm going to put x cosine, or sine, sorry, x sine of theta incident, or theta reflected here, minus z cosine of theta reflected. There's a minus sign there. Then the actual unit vectors, what happens is you're going to have cosine theta incident, and it's going to be positive there, ax, plus sine theta incident, and it's going to be az. Can you confirm this in the book? I'll give you time to read it. Take a look for the reflected field. Or that's the one, the H field. Here.
Yeah, that's right.
Well, I don't.
I've already copied it.
Oh, you did? Yeah, it's in his book on page 362. Just bear with me one last second, all right? Here's what he does next. He wants to get the transmission reflection coefficients, right? So he goes to z, and I'll do this next time. I hate to recopy this whole thing, but z equals 0, that's what he does. And then he says E tan 1 equals E tan 2, just like we did before, and H tan 1 equals H tan 2. I'll give you a reading assignment to do that. Then he gets the coefficients. Now, they're a little different. I could give them to you, and I'm going to go through them, but I'll just tell you this one. For the reflection coefficient, and this is for TE, you can sue me later if you like, you don't like stuff. It's always going to have an eta 2 here, minus an eta 1 here, an eta 2 here, plus an eta 1 there. The coefficient here is cosine of theta incident. Coefficient here is going to be cosine of theta transmitted. Here, the eta 2 is cosine theta incident. The coefficient here is cosine theta transmitted. You can check that, but I know I have to deal with this all the time. All right? And it will reduce eta 2 minus eta 1 over eta 2 plus eta 1 when, in fact, if theta is 90 degrees. Or sorry, when theta is 0 degrees, you can come in and north. I'm sorry I kept you 2 other minutes, but I'm late sometimes.